Alright guys, we are back talking about stats again. Today the topic is measures of dispersion. Measures of spread. That's the way most people term this, and that's how I'll probably say it most of the time, measures of spread. These are ways to talk about how spread out your data are, or maybe how close together they're clumped. If all the data points are really close together, or all they're really spread apart. That's what we want to talk about today. Previously we talked about measures of central tendency. That just talked about ways to describe where the data are located, where the average value is. But here we're talking about the range of the data, or how far they're spread out or close they're clumped together. Okay, these are really useful tools. We'll be using these ideas for the rest of the course, so it's really important that you really get this down. Okay, so let's jump right in here. We have this example here. It says the following data represent the total points scored in each of the NFL Super Bowl games played from 2001 through 2012 in that order. So these are the points: 41, 37, 69, 61, etc. It says compute the range, variance, and standard deviation for these data. Okay, now let's start off easy. Range is super easy. Range is largest value minus smallest value. Super easy to compute. But since it's super easy, it's also not very useful. Okay, so for instance, in this data set, let's see, what's the smallest value? Maybe 31, I think. Yeah, 31. And the highest value looks like is 69. So the largest value in this case, we have largest value is, we said 69, minus the smallest value, which I think is 31. So 69 minus 31, what is 38? And that just tells you, for lack of a better word, the range of your data. It's just how far up apart your biggest value and smallest value is. Now, the problem with range is that it is completely influenced by outliers. For instance, let's say that most of your data, let's say that we added a couple numbers here. Let's say we added a 100, that there was one Super Bowl game where they scored 100 points, and then there was one Super Bowl game where they only scored 7 points. Okay, and so that was we added two values. So maybe we added year 2000 and 2013, and those were, let's just say hypothetically, one of those games had 7 points scored and the other had 100 points scored. Well, guess what? Even though most of the data is, say in the 30s and 40s, the range would not capture that information. The range only captures the information of the largest and smallest value. So if we had 100 was the highest value and 7 was the smallest value, well, the range would be 93. And the range, again, is only based on outliers, okay? The smallest and largest value. They're not necessarily outliers, but they can be outliers. So it's useful in some respect. It tells you the range of your data from smallest to biggest. It's helpful in some aspects, but not terribly helpful. Okay, so that's the range. Super easy. So we're not going to spend a lot of time on that. For here, we found the range for these data. And we want to move on to more helpful measures of spread. Now, the most common used measure of spread is called the standard deviation. Okay, standard deviation. Okay? This is the most common measure of spread, measure of dispersion. And we're going to be using this in pretty much every section from here to the end of class. So it's very important that you get a good grasp of standard deviation. Okay? Now this is just another measure of spread. It's a way to tell how far your data are spread out or how closely they're grouped together. So a large standard deviation would mean your data are really spread out, whereas a small standard deviation would mean the data are grouped close together. Okay. Now here is the formal definition, the formal formula for the standard deviation. It is, let's see, the sum of x minus x. Oh, well, I guess we could. Let's do for. Let's talk about population data first. X minus mu squared divided by n. Nope, capital N. Okay, it's the averaged squared deviations from the mean. Okay, that's how you would calculate the standard deviation. Now this is for a population. Okay. Now here's what I was telling you guys the other day. It's very important that you pay attention to population versus sample hints. You know, if you're dealing with a sample, I'll give you a shortcut formula in just a sec. When you're dealing with a sample versus a population, the formulas are different. Okay? So, for instance, if we were going to deal with the standard deviation, the formal definition for a standard deviation of a sample, it would be the sum of the x minus x bars squared over n minus 1. Okay? That is the standard deviation for a sample. Oh man, I can't write today. Okay, so yeah, for a population sample. And now if you mix these up, if you use the wrong one, you're going to get the wrong answer. So it's very important that you pay attention to what the text says. For instance, the text here says this is the data regarding points scored in Super Bowl games from 2001 to 2012. Now, do you think it doesn't say population or sample anywhere? So you have to kind of figure out, is it a population or a sample? Is it population or sample data? Well, think about it. Has the Super Bowl been going on? Was it going on before 2001 and after 2012? I think so. There was a Super Bowl this year, just a few months ago, so that means it's been going on beyond 2012, since it's 2016 now, and it was certainly going on before 2001, so that means this is sample data. This is not all the Super Bowl games we're talking about. We're only talking about the ones 2001 through 2012. So this is sample data. So we couldn't use this formula here. We have to use, if we're going to use the formal definitions, we would have to use the sample standard deviation formula. Okay. Now we've talked about this notation here. That's sigma notation. That means you want to take all of your data values, subtract off the mean, square them, and add them all up. So that's a several step process here. Then of course divide by n minus 1. So you know, the formal definition, it takes a little bit of work. Now we will come back. Actually, let's do that first. Okay. So what do you see that we need in both of these? Well, we need the mean. So there we need a population mean, but now we're dealing with sample data, so we need the sample mean. Well, this was in a previous tutorial. We did this previously, how to find the sample mean. Okay, so just off to the side somewhere, let's calculate the sample mean. Okay, so the sample mean, remember that's the x bar equals the sum of the x's over n. Okay, so the sum of the x's, now I'm not going to write every little step here, so let's just use our calculator. So we take 41 plus 69 plus 61 plus 45 plus 31 plus 46 plus 31 plus 50 plus 48 plus 56 plus 38. Okay, so that is 553. Now, how many data points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 data points. So we have 553 divided by 12. And the mean is, let's see, 46. Oh, let's see, 0.083 repeating. Okay? So that is our sample mean. Okay? Now, to find the standard deviation for a sample, what we have to do is, let's just create a table. Okay? I'll create a table. Let's see. We're going to have a column that is x bars minus mu. So x bar not x bar. Nope. Oh, I messed that up. Not x bar minus mu. X minus x bar. So I want to calculate each of the x minus x bars. Okay. So let's see here. So we're going to have 41 minus x bar, which is 46.0, let's just say 083. And then we're going to have 37 minus 46.083. Now we're going to do this all the way down until we get to the very end, 38 minus 46.083. We need to do that for each x value. Okay? So when we simplify, let's see what we get. X minus x bar. Okay, so we're going to have 41 minus 46.0. Okay, so we get negative 5.83. That's called a deviation from the mean. That is how far away this value is from the mean. What you get is it's negative 5.83 away from the mean, because it's below the mean. Then we have 37 minus 46.83. That is 9.83 below the mean. Okay? Now let's do that for each of those values. This takes a little bit of time. I'll be the first to admit, but it's not impossible. Okay, so we have 41, we have 37. Now let's do 69 minus 46. Oh, I already messed up. I just realized I typed in my calculator 0.83, not 0.083. So let me back up. Sorry about that, guys. This is what happens, but you have to really make sure you do. You really have to make sure you do this right, or else you'll waste a bunch of time. So constantly be double checking yourself. So 41 minus 46.083. So that's negative 5.083. And 37 minus 46.083. That is negative 9.083. Okay. Oh, let's see here. Okay, now we need to do 69. 69 minus 46.083. Okay, we have 22.917. Now we have 61 minus 46.083. That is 14.917. Okay, then we have 45 minus 46.083. That is negative 1.083. Okay, and then we have 31 minus 46.083. That is negative 15.083. Okay, that was the 31. Then we have 46 minus 46.083. Now that should be easy. That's negative 0.083. Then we have, again, 31 minus 46.083. That was the negative 15 value. Negative 15.083. Okay, then we have 50 minus 46.083. That is 3.917. Okay, let's see here. I'm going to have to move up just a little bit. I think that'll be enough. Okay, that was the 50. Then we have 48 minus 46.083. I get 1.917. Then we have 56 minus 46.083. That is 9.917. Then lastly we have 38. 38 minus 46.083. That is negative 8.083. Okay? So, those are all of our x minus x bars. Okay? Now, what we need to do is square all of these values. Okay? And then add them all up. Okay? So, let's see. X minus x bar squared. Take all these numbers and square them. Okay, so let's see here. Negative 5.083 squared. Negative 5.03 squared is 25. Let's see, how do we want to round here? Let's round to 3 decimal places still, so 837. Okay, then negative 9.083 squared. That is 82.501. Then 22.917 squared. That is 525.189. Okay, then we have 14.917 squared. That is 222.517. Okay, then we have negative 1.083 squared. That is 1.173. Oh, that's really messy, sorry. Okay, then we have, let's see, it's negative 15.083 squared. So we have 227.497. Okay, then we have negative 0.083 squared, and that is 0.007. We have 15.083, or negative 15.083 squared. Remember, that's that 227 figure. So 227.497. Then we have 3.917 squared. So 15.343. Okay. Then we have 1.917 squared. That is 3.675 squared. Or excuse me, that is squared already. Sorry. Then we have 9.917 squared. That is 98.347. And lastly, negative 8.083 squared. 65.335. Okay? There, that is all of the x minus x bars squared. Okay, now what does our formula tell us to do? It says to add all of those up, then all I have to do is divide by n minus 1. Okay. So let's go over here. So we have, and again, I guess I should say this, the symbol for a sample standard deviation is S, and for a population it is sigma. Oh, let's make that a little bit bigger. It's a lowercase sigma. Okay, so sigma is population standard deviation. S is sample standard deviation. So over here, S is going to be equal to the sum of the x minus x squared. Excuse me, x minus x's. Oh, I can't say this. X minus x bars squared. So we need to add all those up. So let's see what that is. Then we're going to divide by n minus 1. Well, that's easy. N minus 1, we said n is 12, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, so 12 minus 1. And this, the sum of all these go in the numerator. So let me add all those up real fast. I'll start from the bottom since that's what I have stored in my calculator. 65.334 plus 98.347 plus 3.675 plus 15.343 plus 227.497 plus 0.007 plus 227.497 plus 1.173 plus 222.517 plus 525.189 plus 82.501 plus 25.837. Okay, now the sum of all of those is 1,494.917. Okay, so the numerator is as such. Denominator, that's easy. That's 12 minus 1 is 11. So divide by 11. And I get 135, let's still round a 3, I guess. 902. Okay? And there is our, I just made a big mistake. Okay, let me back up, guys. I just realized all of this is labeled wrong. I don't know where my mind is. Let me do some erasing. Nope. Alright, I made a big mistake. This is all variance. Variance, okay? Variance, okay? S squared. Now, to find the standard deviation, you have to take the square root of the variance. Sorry, I'll put an annotation in there that I'll put an annotation in there, and we'll have to point that out. But sorry about that. That is variance. I can't believe this entire time I wasn't even thinking. Okay, so variance is this formula. Now to find the standard deviation, okay, standard deviation, that is the square root of variance. Okay? So here's the variance. Now we just need to take the square root. So S equals the square root of 135.902, which equals, oh, let's see real fast, 11.0658. Okay, so there is the standard deviation. Okay, sorry about that. Sorry about that big that big mistake. This is the formal definition for variance, not standard deviation. To get the standard deviation, all you have to do is take the square root of both of those. So square root of this one will get you population standard deviation. Square root of this one will get you sample standard deviation. You have to get the variance first. Okay, now that is a super long process. You don't want to do that. Okay, most likely. And that's how most textbooks show you how to compute the variance and standard deviation. Now, let me give you the shortcut formula. Okay, shortcut formula lets you get away from most of that calculation, creating all these crazy tables. Okay, so I'm going to write down the shortcut formula, and let's just do standard deviation. And remember that if you find the standard deviation, all you have to do is square it to get the variance, and vice versa. If you want to find the variance, all you have to do is take the square root to get the standard deviation. So shortcut standard deviation. Okay, that would be, okay, now we're talking about a sample here, so you'll have to consult your book to see how the changes are for population. But for a sample, S equals the square root. Okay, it is, let's see here, it's the sum of the x squareds minus the sum of x squared divided by n, and then everything over n minus 1. Okay, let me actually make this go down so we don't have any confusion here. That square root goes over the entire thing, numerator and denominator. Okay. This, I think, will allow us to find the standard deviation a little bit faster. Okay, not a ton faster, but a little bit faster. Okay, so the only difference, now this is for a sample. The only difference if this was a population is there would be an n on the bottom instead of n minus 1. Okay, so we have the sample standard deviation formula here. Now, if you want to find variance, like s squared, not s, so not the standard deviation, but the variance, just remove that square root sign, and that's variance. Okay, so let's see here. So to find, for this particular example, we want to find the standard deviation using the shortcut method. Okay, let's figure out here. Well, n minus 1, that's easy. We already know that. That's 11. Now we need to find the sum of the x squareds, and we need to find the sum of x, and then square that. So what is the sum of the x squareds? Okay, that's if you take all of these numbers, square them, and add them up. So I'm going to use my calculator to do this so we don't have to write a whole bunch of stuff here. That's 41 squared plus 37 squared plus 69 squared plus 61 squared plus 45 squared plus 31 squared plus 46 squared plus 31 squared plus 50 squared plus 48 squared plus 56 squared plus 38 squared. That's the sum of the x squareds. Now this is a pretty big number. I probably should have made my square root sign a little bit bigger, but we'll make do. That is 26,979. 26,979. So minus. Now it's the sum of the x's then squared. So don't get these two terms confused. That right there says take the sum of the, says take all the x's, square them, add them up. This right here says take all the x's, add them up, then square them. We'll get different numbers. Okay, those aren't the same operation. So we need to do 41 plus 37 plus 69 plus 61 plus 45 plus 31 plus 46 plus 31 plus, let's see here, 31, sorry, I lost track, 31 plus 50 plus 48 plus 30, nope, not 36, 56 plus 38, okay? I get 553 for the sum of the x's. Now I need to square that value. And I get, Alright, I'm going to write this down real fast, but I probably made a mistake. I'll let you know why I made a mistake in just a second. Okay, I'm writing 305,809. Now, why would that be a mistake? I had to be a mistake somewhere because that number is 26,979. That number says 305,809. If you subtract that, you're going to get a negative number. Okay, you're going to get a negative number, and then you're going to try to take the square root. You're going to get an imaginary number, which the standard deviation is not going to be an imaginary number. So let me back up and see where I made a mistake. Hopefully I made a mistake just in the last step, but I could have made a mistake with this number here. So let me see real fast. Okay, 41 plus 37 plus 69 plus 61 plus 45 plus 31 plus 46 plus 31 plus 50 plus 48 plus 56 plus 38. Okay? Nope, it must be with this number here. Okay? So let me check that number right there. Alright. Oh, you know what? I'm a big dummy. Maybe I didn't make a mistake. Divided by n. So divided by 12. There we go. I'm just not on my I'm not on my A game today. Sorry guys. Okay, so right here, let's simplify the numerator. So what we need to do is take 26,979, subtract off 305,809, which is divided by 12, and we get 1,494.9016. Let's say 917 divided by 11. Okay, this is starting to look familiar. 14. Oh, look at there. 1494.917 divided by 11. Perfect. Which tells us that S equals the square root of, if you divide that, 135.902, which equals 11.658. So, look here, we got the same answer twice, which means we probably did it right in that case. Okay? So the standard deviation is 11.658. Notice that process took a lot less time than this process over here. So even though most books teach you this way, by the definition, taking the sum of the deviation, square deviations and then dividing by either n or n minus 1, the shortcut saves you a bunch of time. Now, it's not a walk in the park necessarily, but it saves you a good amount of time. Now, what this says is just it tells you how far spread out the data are. Okay. Now, we'll get all kinds of cool concepts about standard deviation as we go through the course. For instance, most of the data, that is, almost 100% of the data, over 99% of the data, are within 3 standard deviations of the mean. So, for instance, what this means is, if you go take the mean, which we found was 46.083, if you add 3 standard deviations to it, so add 11.658, add 11.658, add 11.658, add 3 to it, and then subtract 3 standard deviations, that 99.97% of the data values will be within that interval. Okay. Another cool little fact is that about 95% will be within 2 standard deviations of the mean, or within 1 standard deviation of the mean, you might have about 68%, 68.43, I believe it is, percent, okay, of the data. Okay, so we're going to be using standard deviation a ton, so it's really important that you get this process down. Get this down pretty early, because we're going to be using the standard deviation a whole lot. And I guess while we're at it, let me illustrate what I was just talking about. So let me scroll down here just a little bit. Let me keep X bar. I'll need that. Let's see here. So if you draw, when I say there's 99.7% of the data within 3 standard deviations. I mean, what I mean is, so take X bar, the mean. So X bar, let me change colors real fast. Let's go red. X bar equals 46.083. If I add 3 standard deviations to that number, so 3 standard deviations would be 3 times 11.658. So if I add 3 standard deviations, okay, so if I draw like a number line here, X bar is there in the middle. Let's say X bar equals 46.083. Let's make this a little bit bigger. Okay, let's say there's 1 standard deviation, 2 standard deviations, and 3 standard deviations to the left, then 1, 2, 3 to the right. Okay, so this distance here, that is S. That's S. Okay. Or, like, let's say this distance here is 2S, or this distance here is 2S. Okay, or maybe like this distance here, that is 3S, or this distance here is 3 times the standard deviation. So you could say right here, that is, this value right here is X bar plus 3S. So 3S is just 3 times our standard deviation, which is 34.974. So would be 46.083 plus 34.974. So that is 81.057. And if you subtract 3 standard deviations, you'll get this number. So 46.083 minus 34.974. And you get 11.109. Again, that is x bar plus 3s. And this over here is x bar minus 3s. So, we have something called the empirical rule, which says if you are within 1 standard deviation of the mean, so you're like on this interval right here, within 1 below and 1 above, that there is about 68% of the data. Okay? If you live right here, anywhere right there, that about 68% of the data is going to be there. Okay? Then the empirical rule also says, well, if you're within 2 standard deviations of the mean, so like right here, centered around the mean, of course, there's going to be 95.57% of the data. That's the empirical rule, 95% approximately. Okay? But then the empirical rule further says that if you are within 3 standard deviations of the mean, so that would be like this 11.109 to 81.057, that interval is going to contain 99.097, I believe, approximately 99% of the data. That's the empirical rule. Okay? Empirical rule. Okay, so and you can that's very, very helpful as we go on through the course. There's going to be lots of different times where we're talking about the amount of data that's centered about the mean. Okay, so we're going to do lots of stuff with the standard deviation throughout the rest of this course. Now the variance, like up here, there is your variance formula. As far as we're concerned, the variance is really only ever used to get to the standard deviation. Okay, and of course this is the definition type way to get to the variance. We're going to use the shortcut methods. And of course, remember, if you want to find the variance, and this is all for a sample, remember, sample data here. If you want to find the variance instead of the standard deviation, all you have to do is square both sides. So that equals the sum of the x squareds minus the sum of the x's squared over n all over n minus 1. See all I did right there? To go from the standard deviation to the variance, just square both sides of the equation. Okay, and so you have the variance, which is s squared, equals everything that was on the right hand side without that square root sign. Okay? So again, that is sample variance. Okay, so just to recap here, what we did here is we found the variance using the variance and standard deviation rather by the definition, that is using this definition here. That's the formal definition of variance. That's the way most books are going to teach you how to do it. But our book is kind of cool, and it gives you just the shortcut formula. We verified that both these answers matched up, and then we kind of did some explaining with the empirical rule. Now, I do want to take one quick. Actually, I'll do that in another video. I'll show you how to do this with your calculator. Okay, because this will save you a ton of time if you learn how to do this with your calculator. So I'll do that in the next video, so you don't have to watch all of this to get to that part. So there is variance and standard deviation, and a little bit of explanation about what those things mean. Hope it's been helpful. Of course, let me know if you have any questions at all. See you soon.